All right, last time we spent a fair amount of time looking, last few lectures we really looked at stability criteria, right? We started with an example. We saw that we started with a 3-stage amplifier, simple amplifier, and we saw that it was actually unstable when we applied sufficient amount of feedback to it. As we applied feedback initially, it was stable. As we increased the amount of feedback we applied, it became unstable. And we also saw something interesting there that led us to more advanced stability criteria. We saw that actually when we introduced those two tiny resistors in series with the capacitors, we essentially introduced two zeros, and we had a system where we could have a loop gain that was greater than 1 with a phase around the whole thing of 360. I mean, if you think about the loop gain, it would be 180 because of the minus sign. But it was stable. And then that led us to these more advanced criteria for stability. We looked at the Nyquist criterion, which basically is a graphical way of, by looking at the phase and amplitude and plotting the phase and amplitude of the loop gain, you can actually see whether or not, based on whether or not you encircle point -1, you can determine whether or not you have right half-plane poles and how many, et cetera, et cetera. And then we saw that they have generalizations as nonlinear, in nonlinear systems, right? We saw the circle criterion and off-axis circle criterion that allow you to evaluate it for given types of nonlinearity in the loop and say if whether or not the system is stable. So now we are going to start going back to circuits. We're going to try to see how they apply from a circuits perspective, and we will do a system level analysis first, and then we'll go into the transistor level circuits to understand how these things are applied and what practical implications they have. So we'll start with adding sophistication to the system. So we'll start with some things that are pretty straightforward, and then we will kind of add more complexity to it, and we'll see how it behaves. So as a starting point, let's start with a first order system. So let's say you have an amplifier or a system whose A of S is basically A0 over 1 plus S over omega 1, right? So this is a first order transfer function. And if you look at the loop gain, so if you have, this is your forward path, if you look at the loop gain in a feedback system, so this is basically A of S, and then you have F, and then you have the UI minus and UI plus as we defined before, something like that. We can actually plot the magnitude and phase of this quantity of the loop gain. In other words, the magnitude, or 20 log really of the magnitude, it's a Bode plot, 20 log of F times A of j omega. And we can look at the phase of F times A of j omega. Really, we are doing it versus log of omega to make it a real Bode plot. Now, if you look at these quantities, this is a pretty straightforward plot, right? I mean, you can think about it this way. You can say, okay, well, at low, so for example, it depends on the value of F, right? This is the loop gain. So if if you also plot the magnitude of A of j omega, 20 log of A of j omega. So let's say this is the magnitude of A of j omega. So this is basically omega 1. And then we know that the phase roughly starts from a decade below to a decade above and goes from 0 to negative 90 degrees. So let's say, and at this point, in this system, is going to be exactly negative 45. So you go from a decade below to a decade above, roughly like that, and more practically something round like that. So the phase transitions like this. Now, once you have such a system, then the question, and of course that's what you have. Now, also, if you start looking at the actual transfer function of the system, which is we know that the closed loop transfer function of the system is A over 1 plus AF. So if you look at that really A of j omega over 1 plus F A of j omega, and plot its magnitude, what you will notice is that you have a transfer function like this. And it's easy to see it. So let's calculate this. So if this is A of S or A of j omega, so this is going to be it's a basic calculation, A0 over 1 plus S over omega 1 divided by 1 plus A0F over 1 plus S over omega 1. And then you multiply the numerator and denominator by 1 plus S over omega 1. You get A0 1 plus A0F plus S over omega 1. And if you factor the DC part of the gain, you will get A0 over 1 plus A0F. This is the DC part of the closed loop transfer function. You can easily see that you get 1 plus S over omega 1 times 1 plus A0F. So what you see is that your low frequency gain in the closed loop system is going to be A0 over 1 plus A0F. So it's your open loop gain scaled down by factor 1 plus AF. And your new cutoff frequency, the new omega, is omega 1 times 1 plus A0F. So you can easily see that your DC gain went down by the same factor that your cutoff, that omega, that your 3 dB frequency, or omega h, went up. And their product has remained the same, right? You can see, this is a classic example of a gain bandwidth product, right? So the gain bandwidth product, omega 1 times A0 here, is the same thing as omega 1 times 1 plus AF times A0 divided by 1 plus A0 AF. So, and what happens to the phase? The phase, now this is where your pole is, this is where you go to negative 45 degrees. So the whole phase is basically shifting up this way. So from a purely magnitude and phase Bode plot perspective, this is what's going to happen. So you can easily, so now let's see, is this stable or unstable, this system, as you apply more and more feedback, as you increase the feedback? Well, let's look at the Nyquist plot, right, to see how that looks like. So if Nyquist plot is really the real part of Fa of j omega, which is this quantity, and the imaginary part of F times A of j omega, the loop gain, really, right? This is the loop gain. So now what does it look like? So you start off from some large value, okay? And then how much phase you the maximum amount of phase that you will have is negative 90 degrees. So you will stay in this quadrant, right? So your phase varies from 0 and maximal goes to negative 90 degrees. Your amplitude starts from some value A0. So this is at omega equals 0, and then it goes to 0 eventually. So it would be something like this. So this is where omega goes to infinity. And this is point negative 1. Right? So from a linear standpoint, right, this is stable or unstable? This is completely stable, right? Now you can see that also if you want to think about the phase margin or things of that sort that we talked about last time, we introduced them. So basically this is negative 180. So no matter what you do, your phase, you have at least a phase margin of 90 degrees. So your phase margin is greater than 90 degrees. So the system appears very stable. Now how about if you had nonlinearity? Now we can apply the circle criterion, right? So let's say you have some sort of a nonlinearity that is basically a first and third quadrant. So from a nonlinearity, so let's say you have a nonlinearity that's confined to the first and third quarter, or quadrant, sorry. Some shape with even hysteresis and time variance and all those things, but it's remaining in first and third quadrant. So if it remains in first and third quadrant in general, what is K1 and K2? K1 and K2 are the limiting ranges of these things, right? What is K1 in general for nonlinearity that's in the first quadrant and third quadrant? 0, right? And what is K2? Infinity. So worst case, these are really the worst case scenarios for K1 and K2 for first and third quadrant. So quadrant. So it's K1 is 0 and K2 is infinity. And what kind of area does it correspond to? If you think about it, it's a circle. One end of it is at 1 over 0 here, and one edge of it is at 1 over 0, and the other one is at 1 over infinity. Right? So you have to avoid for nonlinearity, for this kind of nonlinearity, as long as it's confined to first and third quadrant, as long as you avoid the left half plane, or left side of the plot, the negative real part for the loop gain, you are stable. So is the system stable, even with nonlinearity? Yes. So as long as you have your nonlinearity is confined to first and third quadrant, it doesn't matter if it's time varying, if it has hysteresis, if it has memory, things of that sort, it will remain stable. Yes? Yes, well, it could be anywhere. It could be an actual extra element nonlinearity. You can actually introduce it here as some phi dot. So it can be in the system. And this is a criterion for absolute stability, right? Right? Circle criterion is an absolute stability, meaning that you would not even get a steady state fixed amplitude output. The output eventually has to go to 0. It's different from Bibo stability, as we talked about before. Bounded input, bounded output stability. So a first order response is stable. Now, what happens as we increase the pole frequency? As we increase, sorry, not the pole frequency, as we increase the amount of feedback to the pole. So we are starting with a single pole, right? The single pole is at whatever frequency, like omega 1. Right? This is where the pole is originally for the open loop system, or when f is 0. When f is 0, that's where the pole is. Now, as you increase f, as you increase the amount of f, what happens to the pole? The pole absolute value increases, right? It's going to a higher frequency. So what happens is that your pole, essentially, as you increase the f, moves to the left, away from the j omega axis, which means that there's no way for it to become negative. I mean, I'm sorry, there's no way for its real part to become positive or go into the right half plane. So all of these things are very consistent, right? All of these pictures. You see you have a lot of phase margin here. You have, from a Nyquist perspective, you're not getting anywhere near point -1, let alone encircle it from a Bibo stability perspective. From an absolute stability perspective, for any kind of nonlinearity in the first and third quadrant, you basically avoid, as long as you avoid the left half side, you're stable. Your pole, as you increase the feedback, gets pushed out. So it's a very stable system. You don't need to worry about anything. So that's like a first order system. Okay? So no major surprises here, I guess. But it's interesting to notice how this behaves. So now let's go to a second order system. Let's try a second order system and see what happens for a second order system. So keep going. Third order system, fourth order system, fifth order system, till we're on outside. No. So second order system. So what does second order system look like? So A of S is A0. So let's say this has two poles and no zeros at this point. 1 plus S over omega 1, 1 plus S over omega 2. Now let's redo the same things, similar things. So essentially we are looking at the magnitude and phase of the loop gain. So magnitude and phase, so it's 20 log base 10 of the loop gain of j omega, which you can actually write it as f times a of j omega if f is constant, not a function of frequency, but in general it could be, so you can write it as generally as a loop gain with this cap t, special t defined here. So you have two poles, right? So let's say at omega 1 and omega 2. And this is log of omega. So what do you get? From a Bode plot perspective, Bode plot looks like this, right? I mean, you have these are the asymptotes. So you have one asymptote, two asymptotes intercepting here, and intersecting here, and then another pair intersecting here. So what you have here is that you have an amplitude response that does behave kind of like this. Right? And how about the phase response? Well, the phase response of the system, you have, so let's go down to here. So this is negative 90 degrees, this is negative 180 degrees. Each one of these poles will contribute total of maximum 90 degrees, starting from a decade below to a decade above. So you will get something like this here, and then this one kicks in, and then you get another one. You asymptotically reach negative 180. Oh, this is a little bit off. So this is roughly here, roughly negative 45, and roughly negative 135 at these degrees. Why roughly? Because there's residual phase from the other pole contributed at that point. So it's not exact anymore. But it's, as if the poles are not too close to each other, it's going to be relatively accurate. So that's how it looks like. So what is our phase margin? Well, it depends. It depends on where we really hit the gain of 1. So this is, if this is omega unity, then the phase margin is this much. If this whole thing was scaled down and our omega unity were here, for example, this would be our phase margin from a phase margin perspective. Now, whenever we are looking at phase margin, you have to be really careful about those cases where the phase goes down and comes back up and things of that sort, right? We talked about that. We know how to analyze that using Nyquist. So let's look at the Nyquist. So let's look at the Nyquist plot and see. So did we use? Okay. So to keep it consistent with that, how does the Nyquist plot look like? Well, the Nyquist, again, if you look at it, you start from something at omega 0. You start from some magnitude. The magnitude, the R in the polar plot starts dropping. So this is the real part of the loop gain. And this is the imaginary part of the loop gain. And then the amplitude starts dropping, and the phase asymptotically hits 180 or negative 180. Doesn't go below negative 180, right? So that's the way the plot will look like. And if, let's say, if this is point negative 1, so are we stable or unstable based on this from a bounded input, bounded output perspective? We are stable. So we have a bounded input and bounded output. So for a linear system, this system is stable. Okay, fine. And you can also, and then we'll do a little bit more detailed analysis of this thing. How about from a nonlinear perspective? If you look at it from a nonlinear perspective in terms of whether or not it's stable or not. So if we wanted to do something as broad or as general as the previous case, which was we said any kind of first and third quadrant nonlinearity, right? If you go with anything like that, some craziness, etc., I don't know, some time variance, etc., can we say that this is stable? Can we guarantee absolute stability? No, right? Because this corresponds, as we just said, to the circle criterion. Basically, what this would say, the circle would encompass the entirety of the left half side of this Nyquist plot. So you are going into the circle, because the circle is the entire left half side of this plot. So you can't guarantee stability based on this. And in your problem set, you actually saw a case where you have a phase that never reaches 180, right? But with the right kind of nonlinearity, you can actually make it, it's possible for it to oscillate. So when we say it's stable, we really mean in terms of so the phase margin in that case is positive if you think about it, right? You have positive phase margin. But still, a nonlinear, you can generate these nonlinear systems that can produce instability. So in general, this is not going to be guaranteed to be stable. And we've seen a counterexample. But is there some kind of nonlinearity? If we limit our nonlinearity to certain kinds of things, can we say that this is stable? Now, we also had this other criterion, right? The off-axis circle criterion. Right? Can we, what was the additional constraint to use the off-axis circle criterion? Do you remember it? Monotonic, exactly. Having a monotonic nonlinearity. So now let's assume that the nonlinearity is monotonic. So a monotonic nonlinearity. So let's see if we can say something about a monotonic nonlinearity and stability in this case. So in the case of monotonic nonlinearity, if you have a k1 and k2 that are like 0 and infinity, it means that you need to be able, so one of the points is at infinity, the other point is at 0. The question is that can you find a line, essentially, because the other point is that passes through point 0 and is not crossed by this, right? So you kind of can, right, if you think about it. It appears. Well, marginally, right? So if you kind of think about it this way, just like this is maybe this is the line, right? So you're kind of like on the verge of this being able. But now if you, for example, if your nonlinearity is confined, so let's say I have a nonlinearity that's confined to some sort of, let's say, a K1 that's minimum of, I don't know, 1, right? If K1 were 1, right, let's say your nonlinearity is exceeding this 1, then what happens is that you can actually, then you need to find a line crossing across here. That would not be crossed. And that's much easier to maintain. So in fact, if you have a system that's nonlinear and it's unstable, by introducing some additional pathway so it doesn't completely saturate, you may be able to increase K1 above 0 and pushing this line out, which allows you to stabilize the nonlinear system that way. So these are potentially useful things to use. So, and that's why generally it is hard to make oscillators with this kind of second order system, with a system with two like real poles. It's not as straightforward. It's kind of difficult, really. So now let's see what happens if you look at the closed loop and do the analysis. Actually, if you look at let's do a similar analysis. So let's say, well, what is the closed loop transfer function, right? H of s is A of s divided by 1 plus A of s times f. 1 plus f times A of s. So if you plug this thing in, so now you have A0 over those two terms in the denominator divided by 1 plus A0f divided by those two terms in the denominator. And then we multiply the numerator and denominator by those two terms in the denominator. So you will get A0, and then you get, so now what you get here? You get 1 plus s over omega 1 times 1 plus s over omega 2 plus A0f, which you can write, so we can simplify. If you multiply it both by omega 1 and omega 2 as well, so you will get A0 omega 1 omega 2. You're multiplying the numerator and denominator by that. What you will end up is s squared plus omega 1 plus omega 2s plus 1 plus A0f omega 1 omega 2. Okay? So it's just simplifying that. And now the question is that you have a denominator that's a second order, right? So quadratic equation, basically, right? It's not. So the question is, where are the roots of this thing, if you wanted to find the roots of it? So the solution for this, obviously, is a classic quadratic equation, the very basic high school form for that is just this. Right? Over 2. So these are the roots of this thing. And the key question is that you can see that you're starting with real roots, right? So if you start looking at where the poles are and how they move, so this is the sigma and j omega plane for the poles of the closed loop transfer function. So when the loop is, so you have two poles, right? So you have negative omega 1, and then you have negative omega 2. Those two real poles. As f, so this is where f is 0. This is where the poles are, right? If you set basically, and you can see if you set f to 0, this basically reduces to omega 1 and omega 2. The solutions for that, which is where they should be anyway. Now, as you increase f, you can clearly see that this term becomes smaller, right? What's under the square root? Which basically means that the difference between the two roots becomes smaller, because this is what determines how far the two roots are. So the roots start moving towards each other as you increase f. So as you increase the f, so this is f increasing, right? poles of the closed loop system start moving from where they were in the open loop system, and they start getting closer and closer to each other. And at some point, they actually collide, right? At what point do they collide? When this thing becomes 0. When this term becomes 0, so omega 1 and omega 2 are the same. So and that point is basically when you set it to 0, you can easily see that it's basically when f is greater than 1 over a, omega 1 minus omega 2 divided by 4 omega 1 omega 2, if I'm not mistaken. Yes, that's correct. So, or at this point, let's say at this point, this is the point where you have overlapping poles. You have a q of 1/2, you have a zeta of 1, a damping factor of 1. This is where they're colliding. And where do they hit each other? If you look at this, if this becomes 0, it's just the average of the two. It's exactly halfway in between. So they meet exactly halfway in between, and they would be on top of each other. And if you increase the f beyond this, so this is for that value of f. Let's say f critical. Now, beyond this, if you increase the f, then now you end up with a negative term under the square root, obviously. So you get two imaginary poles that have the same real part, which is exactly the halfway point. So the real part doesn't change, but the imaginary part starts increasing. So the poles start moving this way and that way. So you have a pair of complex conjugate poles that are moving away, and they become less and less damped, right? So you go this way. So you have a f, no, this is still f increasing, right? But according to this picture, the poles never go to the right half plane, which is another way of saying that the system is bibostable. The linear system is bibostable, which is consistent with what we saw from Nyquist, which is consistent with what we saw from here, there. All of them should say the same thing. Right? They are different pictures of the same thing. Right? So that's for a second order system, right? So now let's talk about a third order system and see what happens there. So if you have a third order system, and as the order of the system increases, then our ability to do more and more analytical things kind of like goes down, and then we have to rely more on the graphical, the Nyquist stuff, and all those things like that, so, which is good because we already have developed all those things. So the third order system, of course, A of S is some A0 over 1 plus S over omega 1, 1 plus S over omega 2, 1 plus S over omega 3. So 3 real poles, and the Bode plot would be something like this, of the Bode plot of the loop gain. So we are doing the Bode plot of the loop gain, which is basically we are plotting 20 log of the magnitude and phase of the loop gain. And what we have here is something that, so you have a P1 and omega 1, omega 2, and omega 3. Log of omega. So you have something that's flat here, then you go to the first slope, you start at 20 dB per decade, you drop at 40 dBs per decade, you drop at negative 60 dBs per decade, and so on and so forth. And your phase starts from here, here, here. So asymptotically, if there are no zeros in the transfer function, you get to negative 270 degrees. So if I ask you what's the phase margin, you have to say, well, the answer is depends on where you cross the unity frequency. So in this case, if this were actually our unity gain frequency, if this is where it was, this is negative 180. So you actually have negative phase margin in this picture. Now, if instead of this, we were looking at the same plot with reduced magnitude, if f were smaller, for example, we were cutting across here, then you're looking at a tiny phase margin, depending on which way, where it is. It could be positive or negative or something like that. So again, let's do our general analysis. Let's look at it from a Nyquist perspective and see if it makes sense and what we can tell from looking at that. So the Nyquist plot, okay, of this thing, so again, we are looking at the real of the loop gain and the imaginary of the loop gain. More accurate, also kind of like f times a, which is the loop gain. So if you're looking at that and you're plotting this, how would it look like? Now, the plot for loop gain, again, for omega equals 0, you start from here, you go around, you come back, and then you hit it at negative 120, negative 270, right? So you can easily see, well, maybe I went a little too far here. Something like that. So is it or is it not encircling the point negative 1? Right? That's the metric, right? Is it or is it not? Well, you say, where is point negative 1? Right? Well, you can easily see that the scale of this thing, you remember, this is f times a, right? So as I change f, what happens to this thing? Let's say f is just a scalar. As I increase f, it just basically scales up, right? Proportionately, it scales up, this plot, or scales down. So depending on where, you know, your point negative 1 is, so if I say, well, point negative 1 is here, so it's stable for that f. As I increase f, this is going to become a different plot, right? This is going to become this plot, and it can encircle it. Which you can also see in this picture, right? If f is very small, where would my curve be, right? So I would be like, it would be like this. Even from a phase margin perspective, which we know is not perfectly complete, but so in this case, let's say this is omega 1, here we have some positive phase margin, right? If f is small. As we increase f, we are moving to the up higher and higher values of this thing, which basically pushes the cutoff, the omega unity, the frequency at which the gain becomes 1 higher, which then can produce a smaller and smaller and eventually negative phase margins, which is also consistent with this picture. As you scale this up, you start encircling point negative 1, and then you are not stable. So these pictures are consistent. What happens to this, the other picture we had? And in terms of, so now if I ask you about nonlinearity, it's kind of like also a moot point, especially if you are encircling point negative 1, right? So if your linear system is unstable, then you can't guarantee anything about nonlinear system, right? Instability. But again, you may say, okay, well, what if I'm here? Well, from a linear perspective, if I'm on this smaller curve, from a linear perspective, linear system perspective, you're stable. From a nonlinear system perspective, it depends on what kind of nonlinearity you have, right? If the corresponding circle for that nonlinearity looks like this, then you're stable, right? Or if you have a monotonic nonlinearity that allows you to have a circle like this for an off-axis circle criterion, then you're stable.
This is for the original one.
For the original one, not for the big one. Yes, correct. For the small one. Yes, thank you. Yes, for this curve, not this curve. So let me just maybe even get rid of that. Yes, thank you. Right? So we are stable. But if I have in general a nonlinearity that's first and third quadrant and it's not necessarily monotonic or anything like that, essentially all bets are off, right? It may or may be, it doesn't guarantee that it's unstable, but it can definitely not guarantee that it's stable. So those are the kind of things we need to think about. Now, how about the movement of the poles? It has a name, by the way. It's called root locus, because it's a location of the roots, the poles, right? It's how they move. So from the root locus perspective, which we've been doing up until now, without calling it root locus, so where are our poles? So we have one at negative omega 1, one at negative omega 2, and one at negative omega 3. Now, there are rules for determining and drawing. There are ways to determine what the root locus looks like, and they're actually pretty useful if you're looking at root locus. We're not going to go into those rules. We're going to plot it because we're not going to be using it a lot, but they're useful things to know. So the locus will be here, we know that on the j omega axis, on the x-axis, it would be to the left of an odd number of poles and zeros. So that's where it would be. So what happens is that when you look at these two, if this guy was far away, it reduces essentially to this case, right? So when you think about it, these two start again moving towards each other. They have to start moving towards each other. And this guy by itself, if these guys were far, looks like that, right? So this guy starts as you increase the f, it will go that way. And as you increase the f, these guys will start getting close to each other. They will not necessarily hit near exactly in the middle because of now the influence of this other pole. In fact, there will be poles kind of like. So what would happen is that these guys will actually be hitting each other a little bit this way, but that doesn't really matter. So at some point they will start hitting each other, right? As you increase in f. So that's where these two poles start becoming complex. Now, at that point, which is what you have, is that if you zoom into this thing, what do these poles see? They're so close to each other, or very close to that point, that they don't see this third pole. This third pole is at infinity, because they are very close to each other. So in the beginning, their behavior should look exactly like this, right? So they exit at right angles. But poles, kind of like in locus plots, they actually repel each other. You can think about them as like, and they're attracted by the zeros, and they repel each other. And those are part of like the rules of kind of doing it. So that's the way they behave. So what happens is that now, as they are starting to move out, they see the effects of this guy. So they're pushed out. And then as they're pushed out, you can see that eventually they can do what? They can end up on the right half plane side. And that's when you get an unstable system, because you can have a pair of poles that are on this side. Now, if you're making an oscillator instead of an amplifier, right? So you're making an oscillator, one of the ways to think about it is that you're trying to actually get, what are you trying to get if you're making an oscillator? You're trying to get stable, well, stable is not the right word. You want to get reliable pair of poles exactly on the j omega axis, right? If you're trying to get a constant amplitude, something that whose amplitude doesn't change. So what you would need is a system that if the poles for some reason are going a little bit farther out to the right-hand side, it reduces the loop gain and it brings them back in. And if they go a little bit to the left-hand side, it increases the loop gain or increases the feedback and brings them back. So it's a stabilization of an unstable system, right? And that's not actually about using the nonlinearity. We briefly talked about this, and we can talk about it a little bit more, about the amplitude stabilizing mechanisms in an oscillator. But that's what they do. They would kind of push, if it goes this way, pushes it back this way, and the other way around. So it maintains it exactly on the j omega axis, and how you make an oscillator. We'll talk a little bit more about that later. But that's the essence of this thing, right? So you can see now for a system with 3 poles, you can easily get unstable. And now go back to the example, the circuit example we started with, right, for stability. You remember there were 3 capacitors, 3 poles. We introduced 3 poles. And as we increased the feedback, we went from a situation where we had unstable, we had 3 real poles initially in the open loop system. Then as increased feedback, we saw that they were becoming complex because we saw that ringing in the transfer function. And then as we increased it, at some point it became unstable. And then for a bounded input, we had an unbounded output. The step responses started growing in terms of it's becoming a exponentially growing sinusoid, which is basically this system. Right? So that's kind of like what we get from an amplifier. So, but now the question is, what do we do about something like this, or in general, an amplifier? What are the ways to deal with this situation if you are trying to stabilize the system? How do we stabilize an amplifier if you wanted to stabilize it, for example? Well, this goes to what we call classically referred to as compensation, frequency compensation, right? And the way it works is that, let me see. And let me just erase this. Okay. All right, so the key question is that you have a system in general. Let's say you have a transfer function, a loop gain, right, that behaves this way. So you have some amplitude plot, and then you have some phase response. And then you are trying, what are you trying to do? So let's say you are saying at this point, right, I do not have enough phase margin, which basically means that it's another way of saying that if you have a plot like this, that you're encircling point -1, if you think about it. If your phase is more than 180, and it has dropped monotonic, or less than -180, and at the point that you have monotonically been dropping the phase, right, it basically, from a Nyquist perspective, it means that at the point where you had unity gain, you had more phase than 180, which means that you basically had encircled point -1 this way. Unless you somehow magically came back in like this, and that would show in the phase plot as going back up. Right? So if your phase plot is dropping monotonically like this, and at the point where you have a gain of 1 or 0 dB, you have a phase more than -180, it means that basically if this circle is circled with the unit with a radius of 1, this has happened here. It means that you have encircled point -1. And so the question is that what can we do? Are there things we can do to make this, to stabilize this? If this is your loop gain, right? So this is the magnitude, the logarithmic plot of the magnitude of the loop gain and its phase. The Bode plot is 20 log of that. So what can we do to stabilize this system? Can we think about ways to do this? There's a simple way that always works, which is lowering the feedback, right? If you make f smaller, because this is really f times a of j omega, right? So if I make it f smaller, then instead of being on this plot, my magnitude plot would just scale down. I would be on this plot, and then I will have sufficient phase margin. It's basically like tantamount to say, scale this whole thing down, so it would go like that in Nyquist. So you don't encircle the point -1. So this is by making f smaller. But is this what we are looking for necessarily? What's the disadvantage of this way of stabilizing a system? Well, you get more gain. You might get more closed loop gain. You get less loop gain. That's right, right? So what's the problem with less loop gain? The question is that why did we start using feedback to begin with? Smoothing out nonlinearity, increasing bandwidth, all the advantages of feedback. So yes, you're getting less of those advantages. You might as well just like remove the feedback entirely, and then you will not have any problem because your loop gain will be 0. But that's not a very effective way of solving problems. Right? So that's not really the way to go about it. So what can we do? There are a couple of things, right? One is that you can say, look, what if I took this plot and said, you know what, instead of my gain dropping like this, what if I made it drop like that? Right? Or something like that. Or make it go down a little bit first and then, so let's do it this way. So what if I did this? Roughly, I'm just like talking qualitatively right now, right? We'll see how it goes. What if I could do this? What if I could reduce my gain, or here, so that at this point the gain is low, but at low frequencies, for example, here, I still have large loop gain. So at least I will get the benefits of feedback at low frequencies, right? But I would not let this loop gain to be too large at high frequencies. So basically, I'm saying that at low frequencies, keep it high, but at high frequencies, kind of like drop it. System. That would improve my performance, right? It can stabilize the system. What else can I do? Let's say I wanted to stay on this blue curve. Can we do something to the phase part of this thing? Well, if somehow we could push this phase part up before it goes down, right? So eventually if it goes down, that's fine, but we say, okay, well, I push it out temporarily here, so it does not, by the time I'm getting to point unity gain, I'm still high, and then after that it can do whatever it wants. That's another way of doing that, right? So, and you can imagine, how would you do something like this? How would you, what would be the elements that would allow you to kind of kick the phase up? A zero, exactly, right? It has to be a left half plane 0, exactly, very good. Yeah, it has to be a left half plane 0. If you can introduce some sort of a left half plane 0 here to do this, then it's fine. Usually, when you do it circuits, if you want to introduce a new 0, you usually introduce a new pole. So you need to produce a 0 that would happen here and a pole that happens later when it doesn't matter as much. But you have to remember, I mean, that pole and the poles and zeros have a little bit of a long reach in terms of their phase, right? It's a decade below to a decade above. So you need to adjust these things accordingly. So these you can name them different things. But the key question is that if you wanted to make sure, let's say for now, let's make it a little bit more quantitatively, just a little quantitative, just a little bit. So let's say you look at this and say, I want to get a phase margin of 45 degrees for the sake of argument. Now, 45 degrees is generally not enough. You typically want to kind of, then you design, you want to kind of have like 60 degrees or something like that. Depends on what you're designing. Sometimes it's enough. But let's say you want to fit 45 degrees because 45 degrees has an interesting property that we can use. And then we can make adjustments around it. So a lot of times we start our design with 45 degrees. And then we make an adjustment later on to make it a little bit larger. But so let's say you wanted to get something like that. And you had a response that was like this. So you had a pole here and a pole here, right? If I wanted to see what is the amount that I need to reduce the gain at the unity gain frequency, or where should my unity gain frequency be, if this is my amplitude plot and this is my phase plot, where is it that I get my 45 degrees or phase margin? Around this point, right? Around the second pole. Or let me speak about it this way. Around the first non-dominant pole. If the other poles are not too close. If the other poles were too close, their phase contribution will just add to this too. But let's say that they're not too close. So if you look at it, at this point, I have a phase of negative 135 degrees, which gives me about 45, I mean, approximately 45 degrees, because there's contributions from this. And whatever poles you might have afterwards. So you can see that if I wanted to now modify this system, one of the things I could do is just, for example, reduce its bandwidth, right? I can make it so that it behaves like this, but it goes flat. So this is basically another way of doing that purple plot. If I could reduce the bandwidth of the system, namely moving this omega to here, omega 1, if I could move omega 1 to that point, what would happen? Well, in the phase plot, of course, the phase contribution of this part will shift to the left, right? The amplitude starts dropping earlier. But as a result of dropping earlier, you start hitting omega 2, the unity frequency at a lower frequency. So if I were to put this unity frequency around omega 2, I should expect to get roughly 45 degrees of phase margin. So after this is done, you can see, so now this is an important thing. You can see after the frequency stabilization of this sort is done, the unity gain frequency is really determined by what to first order? By the first non-dominant pole. So it means that when you're designing an open loop system that you intend to use in feedback, right? You need to think about what your first non-dominant pole really is, because that's going to affect you. So you remember very early on, when we were this was essentially many lectures ago, right? When we were talking about designing an op-amp. We said we want to minimize the number of stages where we get gain out of, right? Because those are where you have, how did we get gain? How did we get high gain in system? The way we did high gain was high voltage gain was by generating these nodes that have high impedances and driving them with something, right? We created these high impedance nodes and we drove them with something, with some drive capability, some GM, and then we got the gain. And when you have a high, and then later on when we talked about time constants, we saw that where the resistance seen by capacitors is what determines the time constants. So if you have a high impedance node, it will have a large time constant, which means that that corresponds to lower frequency response. If they were uncoupled poles, then it would correspond to a lower frequency pole, right? So you remember also we said something along the lines of we try to minimize the number of gain stages for the reasons that will become apparent later. Well, later is now. Okay? Because what's happening is that if you think about it, and we said we try to not go above 2 gain stages if we can. Because 2 gain stages will give you 2 dominant poles in this form. And if you have these 2 dominant poles, I mean, that's this simplified picture, then it means that you really don't want to create a situation where you have too many of these poles. And then remember, when we went to 3 stages of gain, when we talked about, for example, here, a third order system, then we saw that we can easily go to a situation where things become unstable. That's why we are trying to kind of, I mean, it's not a hard and fast rule. There are people who make op amps, and people have made, and I have made op amps with 3 stages of gain and things of that sort, but you need to really be careful about how you do that. So it's not that it absolutely cannot be done, but if you're doing something vanilla, you need to be careful about that stuff. Ooh, wrong. Wait. Okay, so that's one thing. So you want to minimize the number of gain stages if you can. That's the first thing that you want to kind of like think about. Second thing is that once you have minimized those things, you shift this frequency back so that you can actually use it for compensate. You can actually change the cutoff frequency, the unity gain frequency, in such a way that you have sufficient gain and sufficient phase. I'm sorry, sufficient phase margin. Right? Now we'll see how we do this in circuits in a few minutes. But the key part of this is this viewpoint, this picture. But keep in mind, this is phase margin is a simplified picture. You really, if you see some funny things happening with your phase, you really need to think about the Nyquist. And if you have nonlinearity, you need to now think about circle criterion and off-axis circle criterion when you apply that. Okay? Any questions?